Hello, I'm here. All right. Still getting used to this microphone. Here we are. We're on chapter 6. We're not even close to being done with Actually, wait, I'm sorry. We are pretty close to being done with part 1. This is the last chapter in part 1 of this book. So that's pretty good. Here we are. We're talking about Ethernet. And specifically today we are on the Power over Ethernet chapter. Don't you dare ask me about banana peels. I'm not going to eat a banana peel. No way. There is no way I will eat a banana peel. I won't do it. I would have to have a gun to the head to eat a banana peel. Or pineapple skin while we're at it. Bouchon. Yeah. All right. Power over Ethernet. I think I started this last time, right? So we know generally what PoE is, right? It supports devices with pretty low power requirements, although in recent years we've had upgrades to the standard that have allowed us to have things like PoE Plus and PoE Plus Plus that just keep adding on to like the amount of safe power we can provide to devices on the other end. Yeah, okay. So we talked about the general like wattage, the benefits of PoE. I'm not going to go back over because that's fairly obvious, I think, to us at this point. Um, we had some terminology that I was previously unfamiliar with. So we have power source equipment, PSE. It's the device that actually powers the thing that's connected to it over the twisted pair Ethernet cable. And then the powered device is the thing that's being powered by the PSE. And so we have some examples here of powered devices, cameras, access points, phones, etc. And we have our endpoint PSE. So like right here. So this is like what we're talking about in general. Now underneath it is the diagram where we're talking about, okay, so sometimes you don't have, I think this is the situation where you may not actually have a switch that's PoE, but you have devices that can work on PoE or only work on PoE. And so in order to make that shit work, you have a power injector mid-span PSE. So the PSE is actually this mid-span little guy right here. And he's providing the PoE capabilities while also connecting those devices and the Ethernet switch, allowing them to still connect to each other. Yeah. And then we also have a PoE splitter, which will allow us to work with a PoE power sourcing equipment, so switch, like a PoE switch, for example. You can connect with a PoE Ethernet cable to the single port PoE splitter, and that single port PoE splitter can support another single device that does not use PoE but does want to be powered. And so it actually splits up the power from the Ethernet cable into an actual power cable, right? And an Ethernet cable with data so that the device on the other end can use it. Okay, so we had all these parameters. We talked about wattage. I quite honestly don't care. It was like really low at first. We have type 1, which is low voltage, low power, low maximum power provided by our PSE, and then type 2, which is higher on everything. And then we learned about detection, classification, operation, which are just the states of doing things that PoE has. So you have an idle state where you're just sort of like unpowered and there's nothing on the other end, but the PoE device, the PoE switch, for example, would check periodically to make sure there's something on the other end, and that's the detection state. Once something is actually detected, it probes that thing and it tries to classify it as, what type of device is this? Does it need a certain current level? And what is that? And how do I provide it? If there's enough power, so if the PSE is actually capable of powering the device, because it may not be, and the PSE will start the operation phase by actually sending a current over that link and powering it. And then it monitors it throughout the operation phase to make sure that everything's good. how does the PSE know what's on the other end of the cable? If you just sort of throw power onto that cable without double checking, then you could actually damage what's on the other end if it's not PoE equipment. So it, let's see, the example they use is an analog telephone, which could be sensitive to power on its cable connection. So it could actually cause a problem if it's connected to a non-Ethernet device. So the power detection is, sorry, my brain just had like a weird little zap actually. I wonder if it's because I'm talking about electricity. Anyway, sorry. Do you ever get brain zaps where like you have a weird sensation physically in your head? Nope, just me? Okay. Okay, so basically power detection, we're sending like a tiny little bit of electricity over the link, just a tiny bit, not enough to like power anything, but it's just trying to measure the current flow and how much resistance is on the other end. And a certain amount of resistance provided by a device on the other end that works with PoE, that is what is the signal to the PSE, like, hey, I work with PoE, send me power. And then it will actually try to classify that device and move forward, right? So the classification, I've forgotten quite a bit about this. Let's see. There are two power classification mechanisms used, physical layer classification and data link layer classification. So the type 2 PDs that require more than 13 watts have to support the data link layer classification, but it's optional for all other devices that are not type 2 powered devices, which are the, if you remember, they're the stronger, the ones that require more, Type 2 means requires more. The PSE can send more power and support more power needed from the PD in general. If both classification systems are supported by the PSE and the PD, then the information provided by the data link layer classification takes precedence over that from the physical layer classification. Okay, so if it supports type 1 and type 2, we're going to go with type 2. Boom. If a PSE has multiple ports, the typical approach is to probe one port at a time, classify the power required, ramp up the power to the required amount, and move on to the next port until all the power that can be provided by the PSE is allocated. This makes it possible to bring up a port at the full power level supported for a type 2 PD, for example, and then negotiate the actual power level needed by the PD using the data link layer classification system. That's pretty cool. Okay, right. And then the physical layer classification method, it can actually, sometimes the PSE doesn't support classification, which is interesting. The type 1 PSE. Then it's just going to send it straight up full power, which is 15.4 watts, whenever it detects a PD on the other end. Most vendors now use PSE controller chips that provide a power management capability to actually classify power requirements on a link. So I guess type 1 PSEs that don't support classification are probably pretty rare, I'm assuming. Someone asks, okay, but stupid question, I might have missed it. How does the Ethernet transfer the power? You can't do full duplex. You can't do full duplex. Well, you can. Actually, we haven't talked about like half or full duplex in relation to PoE yet. But it basically transfers power by just sending it. Just actually, I think as far as the book has gone so far, at least, it has literally just said it's sending power over the, like it's just sending a current, a certain voltage over the link, and that's it. It just goes over the Ethernet cable. But let's go back up because I can't properly answer that and I'm concerned about it. Oh, interesting. Javier says we can do FTX and PoE together. Okay, here we go. We'll just start from the beginning just to make sure we understand if it said something more specific, that it's here. All right, carefully designed to provide both power and Ethernet data over the same cable without causing any interference with the data. Supports devices with relatively low requirements for power, avoiding the need to provide a separate electrical circuit for the connected device. The power being provided is classed as safety extra low voltage. So it's super low voltage. The power being provided over the Ethernet cable is carefully engineered so as not to present a shock hazard. This still doesn't fully answer your question, though. I think the best we're going to get, at least right now, is it sends a current over the Ethernet cable. I mean, if you... I don't totally understand it either. Because I thought we were already sending a current over Ethernet, and that's what, like, it was electric bits and stuff, right? So I don't totally understand how we're differentiating that current from a current used to just power the device on the other end, right? I don't think it hasn't talked about a special PoE Ethernet cable. I'm pretty sure it just talks about this is power over Ethernet because it works on Ethernet cable. There hasn't been anything mentioned about a specifically made type of PoE cable. Let's see. Yeah, it really hasn't gotten quite as deep. Let's see. This is history stuff, benefits. Let's keep going. Maybe it talks about it more in depth. I would like to know. Let's see. I think I went too far. Hang on. There we go. Classification method. Let's see. A type 2 PD presents a signature that indicates that it's a class 4 device. Okay, hang on. So we have classes of devices here. Remember this a bit. The POC determines which of several current levels is required by the powered device before actually providing the full voltage and power levels to the link. After the classification process completes, there is a ramp up process that increases the power to the level determined by the classification process. So here's how we classify things. We have classes 0 through 4. 0 is basically, you don't really know anything about it, so you're just going to send your full, like, wattage. Type 1 anyway, 15.4 watts. Yeah. Technically, this is class 0 is classification unimplemented. We're just going to send the full bit because that way you can cover everything. Class 1, your current in milliamps is 9 to 12. Your minimum watts at the output of the PSC is going to be 4 watts. Your watts at the powered device will be between 0.44 and 3.84. This is super, super, super low power. And then we just ramp up to class 2, which is a 17 to 20 milliamp current, minimum of 7 watts at the PSC. And then once we get to the PD, we're going to be anywhere from 3.84 to 6.49 watts. Also low. Then we get up to 26 to 30 milliamps, 15.4 watts, that full type 1. That's the maximum type 1 wattage that can be sent. Watts at the PD will be between 6.5 and 12.95 watts. That's medium power. And then our type 2 devices are considered high power. So they can be anywhere from 36 to 44 milliamps of current. Minimum watts at output of the PSC would be 36, and then 12.95 through 25.5 watts at the powered device. That was just me explaining a whole fucking table that doesn't really matter. Basically, a type 2 has its own signature that tells the other end, hey, I'm a class 4, I'm a high powered device. A type 1 PSC treats a type 2 PD as a class 0 device, which makes sense because they take a lot of power and you can just sort of kind of try and hope, right? Our watts at the PD, the highest number we can get apparently-ish is 12.95, and serendipitously 12.95 is the minimum number of watts we might need on the PD end. So if we have a type 1 device trying to power a type 2, it's possible it could work. Probably not super great, but it could potentially work. A type 2 PD that doesn't receive the class 4 physical layer signatures may choose not to start, or must start at a power level of 13 watts and request more power via the data link layer classification system after startup. So it may not work out if we have a type 2 PD with a you know, anything under a class 4 PSE. Okay. You missed the fruit, Andy. How dare you? It's okay, I recorded it. I'll post it somewhere. I'm not sure I really want to put it on YouTube, but I guess I will. Hey, Wookie Mitch. How's it going? Welcome. Y'all did miss the fruit. You did miss the fruit, and I'm sorry. I'm sorry. Here's proof. I ate the rest of the strawberry, but this is proof. Yeah. It's not the worst thing in the world. I'll give him this. Once you get past the hair touching your mouth, chewing it's not the worst. The strawberry was really bad, though. The strawberry was gross. Okay. Kiwis are tart as fuck, though. Okay. I don't think I want to go back through this layer 2 classification method. Actually, no. Yes, I do. It's interesting. Why did I say that? So, it's actually based on LLDP, the way we figure things out at the data link layer for PoE. So, we're transmitting actual LLDP packets with, quote, organizationally specific TLVs, where TLV means type length value. They're in the standard, whatever. The LLDP packets allow the network management functions supported by the PSE and PD to advertise and discover the power requirements of the powered device. The 802.3 AT extension defines LLDP information packets that can advertise this information between the two devices. Type 2 devices are required to do both Type 1 physical layer classification and the data link layer classification. The Type 2 device will use the physical layer classification system to identify itself as a Class 4 device requiring high power. Okay? Type 2 device shouldn't draw more than 13 watts if it hasn't received a sign from the other end that, hey, I can power you at that level. Type 2 powered devices that can operate with less than 12.95 watts must be able to be powered by a Type 1 PSE. If a Type 2 PD can't operate at less than that, when it's connected to a Type 1, it has to indicate to the user that there isn't sufficient power available over the link for the device to function correctly. The LLDP packet exchanges also provide an optional capability to dynamically adjust power requirements after the initial detection and classification phases. Dynamically adjusting power can help manage the total amount of power that must be provided by a PoE switch on its Ethernet ports to meet the needs of the PDs, making the system more efficient. Makes sense. It's like auto negotiation. Note that the dynamic power changes are not designed for rapid variations. A PSE may take as much as 10 seconds to respond to a requested power change. Okay. Scroll up a bit here. Mutual identification. The interrogation and power classification functions make it possible for the PSE and PD to provide mutual identification, in which each determines whether it's connected to a Type 1 or Type 2 device. Mutual identification also provides useful information for devices that support power management features instead of purely automatic PoE. If a PD or PSE does not implement classification, it won't be able to complete a mutual identification process and will only be able to perform as a Type 1 device. So you have to be able to classify if you want to be a Type 2. All right, link power maintenance. Once the detection and classification processes have completed, then the PoE link is operational and the PSE is providing power over the link. The PD provides a maintain power signature, or MPS, consisting of both the current draw used by the PD and a specified input impedance, which can be sensed on the cable pairs by the PSE. This makes it possible for the PSE to monitor the link for the continued presence of an active PD. If a loss of MPS is detected, then the PSE will quickly remove power from the link and return to the detection process of monitoring the link for the presence of a PD. So it's pretty smart. It seems pretty efficient. We're not using more power than we need to, if we can help it. and we're negotiating with other devices to make sure we're not frying them, but we're also like, only sending them what they need. Okay, power fault monitoring. While providing power, the PSC also monitors the link for various fault conditions, including under and over voltage conditions and under and over current conditions. When any of these conditions is detected, the PSC will shut off DC power to the link and go back to the power detection phase. Okay, also efficient. Power shutoff is designed to happen rapidly in a maximum of 1/2 second. This helps to avoid supplying power to a cable that's been disconnected and is then quickly reconnected to a different port in the cabling system. Okay. PoE and cable pairs. The PoE standard specifies the way that power is injected into... Oh, here it is. Here it is, D-Train. I think this is your question. Okay. The PoE standard specifies the way that power is injected into the Ethernet cable pairs and which pairs should be used. Power is injected using one pair of wires. Sorry, my microphone is bothering me again. I just can't figure out... Is my voice super loud when I talk like right into it? Still getting used to it. All right. Okay, so let's see. Power is injected using one pair of wires to carry the positive current, or the plus, and a second pair to carry the negative, or the minus. This provides 2 wires to carry the positive power and 2 wires for the negative power, which helps reduce resistance and heating effects. The standard defines 2 alternatives for which cable pairs are used. Interesting. Okay. Alternative A uses the data signal pairs, which is wires connected to pins 1, 2, and 3, 6. Power is placed on the data pairs by connecting the DC power supply to a center tap on the internal signal coupling transformers. I don't know what the fuck those are. An approach that's called phantom power. That sounds cool. I'm going to read that again because my brain just doesn't understand it. Power is placed on the data pairs by connecting the DC power supply to a center tap on the internal signal coupling transformers. I don't know what internal signal coupling transformers are. I'm not going to lie. Okay. So that's option A. Option B uses the spare pairs, which are the ones that are not being used for data, pins 4, 5, and 7, 8. The spare pairs are so called because they don't carry data signals. Now, this is not true for gigabit, but they don't carry data signals for 10 base T and 100 base T systems. When the spare pairs are used, the power is coupled directly to the wire pairs with no need for a transformer. Note that all 4 pairs are used to carry signals in the 1000 base T systems, meaning that transformer coupling is used on all 4 wire pairs, and that the only difference between alternatives A and B in 1000 base T systems is the choice of cable pairs that are used. Okay. Some vendors have developed their own 4-pair systems of power over Ethernet. These products are based on vendor-developed, quote, standards, and typically require that the equipment at both ends of a PoE Ethernet link come from the same vendor or group of vendors. A new IEEE standard that's currently under development, this was in 2014, so 7 years ago. We're probably good. Will provide a vendor-independent 4-pair system of PoE that will interoperate with any vendor's gear that follows the IEEE standard. What are we talking about there? Because that has to be out by now. It's been 7 fucking years. Provide a vendor-independent 4-pair system of PoE that will interoperate with any vendor's gear that follows the IEEE standard. What is that? Can anyone tell me? Is that... That's not PoE Plus, because they talk about it here in this book, and they call it PoE Plus. Does PoE Plus Plus do that? I'm really curious. Damn, I don't... Someone needs to make a 3rd edition of this book, because it is so out of date at this point. All right, for a power sourcing device, under the current PoE standard, either alternative can be used, but not both. The powered device must be able to accept power on either the alternative A or alternative B wiring scheme, as the PD cannot know which pairs the PSE may use. Javier, my question is, so where the green lemur is right there, it says a new IEEE standard that's currently under development will provide a vendor independent 4-pair system of PoE that will interoperate with any vendor's gear that follows the IEEE standard. So I'm wondering, since this book came from 2014 essentially, if that's out and that's been done and what that is called. Okay, so for power PSE under the current PoE standard, we can use A or B, but not both. The power device has to be, so A or B, again, the differences are basically like, it's which pins we're using for the current, the electrical current. The power device must be able to accept on either the powered device must be able to accept power on either A or B wiring scheme, as the PD can't know which pairs the PSE will use. Also, the PD must be able to accept either current polarity, so positive or negative, on a given wire pair. That's because there's no way to guarantee which polarity of power will end up on which PD wire pairs. Given that the switch port may implement automatic signal crossover, or MDIX, or that a patch cable wired to provide a crossover may be present in any given Ethernet link. Therefore, the PD contains circuitry that automatically accommodates all possible wiring variations with respect to which pairs are carrying DC power, as well as all possible variations with respect to the polarity of the polarity of the current carried by any given pair. It's interesting. The PD contains circuitry that automatically accommodates all possible wiring variations regarding which pair is carrying DC power. Okay, Javier says that's old info. The standard's in use now, so you can, for example, power a Cisco phone on a Ubiquiti switch. So is that just like an extra, like, addition to the standard, basically? It just went into PoE? Like, it didn't turn into like a specific alternative flavor technology of PoE or something? Hi, Julian. How's it going? What do I study? Right now I'm studying Ethernet. Yeah. So a little bit of electrical engineering is thrown in here, but I'm a network engineer. So that is why I'm studying Ethernet. Okay, so here, ooh, we're getting fancy with the diagrams. I just want to say today, guys, I cracked open a proprietary box and got to program basically the ASIC. It was really cool. It was really just pressing a bunch of buttons, but it was still really cool. And then I put it all back together and it was really fun. And I feel like I'm an electrical engineer now. Hooray! Let's see. So this figure, what are we looking at? Okay, so we have alternatives A and B shown here. So because 10 base T and 100 base T standards only use 2 pairs, the 1, 2, and the 3 and 6, we're using, well, I'm sorry. So for one of them uses data on like 2 pairs and then on the other 2 pairs. So here 1, 2, and 3, 6 are used for power. So let's see if we can parse this out. We have a PSE over here, and we have our powered device over here. And then we've got in between them our wire pairs. So yeah, let's see. 4 and 5, 1 and 2. So how is this different? Hang on. 8 days, 6, 7, 2, 3. This looks the same to me. What am I missing? I know what they're trying to like get across, but I don't see a difference in the diagrams. Like, you'd think there'd be color or something. Thanks, Javier. Javier's awesome. Just straight up from Cisco, knows all the things. Powered end is different. Oh, the powered end is different? Hang on. 2, 3, 6, 7. Well, but they look the same. They're labeled exactly the same. I'm trying to... Hang on. Well, let me go down because it'll probably explain it, huh? I just don't see... Oh, I'm stupid. Look. Look, it's literally showing... Oh, yeah, okay. I got it now. I was blind. But now I see... Okay, so in the top one, we've got our PSE and our PD using just the pairs here. Versus on alternative B right here, we've got these pairs 4, 5, 7, 8 being used for power. I assume that's indicating it's using that for... Wait, data or power? This is so confused. I'm sorry, the diagram confuses me a bit. Both switch port and power. Yeah. It's just weird because, okay, it looks, I guess the power sourcing equipment connecting to what spare, like the pairs here means that it's obviously the electrical current being used to power the device are going over these pairs. So we're using spare pairs 4 and 5 and 6 and, or sorry, 7 and 8. Down here, you can see the lines drawn from the powered device and the PSE up to those, the two pairs, 4 and 5 here, 7 and 8 here. But then up here, we don't have that, right? We actually have lines from the PSE down to these pairs right here, the ones being used for data. So we can use them on the data pairs or we can use them on the non-data pairs. Whatever, apparently. I hope I'm interpreting that right. Alternative A has the power going on the same cables as the data. Okay, cool. And then here we've got 1000 base T, my sweetheart. Yeah, so we're using all 4 for data, but once again, you can see we're using all 4 for data and power. So we're connected up. But why do we have an A and a B? See, now I'm struggling with the difference between these two pictures. 1000 base T endpoint, PSE. Multi drawing has a mistake on this one. Okay. All right. What's the mistake? What do you think, Javier? 10100 drawings. Sorry. Here, I'll zoom out a bit. Then we can see the whole thing at once. We're tied into pair 2 and 3. Actually, 1, 2, and 3. Oh, hang on. Yeah, no, that's right. I don't think the lines are going to the center tabs on the powered end stations. Should be there, but I'll look this up too. Oh, okay. Center tabs on the powered end stations. Okay. Yeah, I don't know. Oh no, what am I doing? I don't want this comment. Get out of here. Yeah. We'll keep moving through it, but please feel free to jump in, Javier, anybody else who knows about PoE. Okay. Okay, I do see some differences now that I'm looking. Like I'm noticing we have, yeah, okay. So the PSE on the left side over here is using, looks like pairs 4 and 5 and 7 and 8. And then on the PD side, we're using all 4 pairs. The wiring schemes used for mid-span devices look much the same, with the major difference being that the mid-span device is inserted in the cabling path between the Ethernet switch and the powered device. The midspan device contains the DC power supply and injects the power into the Ethernet link using the same alternative A and B wiring schemes as for 1000 base T and 1000 base T links. Okay. PoE and Ethernet cabling. Zoom back in a bit. The original 802.3 AF PoE standard was designed to operate over Cat3 cabling, which was defined as having 2 pairs available for use by Ethernet signals. The 802.3 AT extension to the PoE standard specifies Cat 5e cabling or better. This is more formally referenced as Class D or better cabling as specified in the international, I'm not going to read all that, standard. One technical issue with power over Ethernet is that it causes a small amount of heating of the cable to occur due to the resistance of copper wires interacting with the DC power being carried over the wires. The slightly elevated temperatures don't present any safety risk or risk of damage or premature aging of the cables or connectors. When many cables are bundled together and all cables are carrying maximum amounts of PoE power, however, the small amount of heating becomes more significant in that it could affect the signal carrying characteristics of the cables in the bundle. Along those lines, it's important to note that Cat 6 and 6A cabling both have thicker copper wires than Cat 5, and that thicker wire results in lower resistance to DC currents and therefore significantly less heating. Some tests indicate that the amount of heating in Cat 6 or 6A cables is approximately 50% less than Cat 5E or 5 or 5E cables. By the way, tests also show that there's no problem using shielded twisted pair cables to carry PoE, and that the foil or stranded shielding actually helps the cable to dissipate any heating effects. Interesting to know, for sure. All right, modifying cabling specifications. The development of the 802.3 AT standard included careful consideration of what happens in large cable bundles with PoE enabled on all cables. However, the cabling standards are not part of the IEEE standards, and cabling specifications are not the responsibility of the IEEE. The IEEE standard does note that, quote, under worst case conditions, Type 2 operation requires a 10 degrees Celsius reduction in the maximum ambient operating temperature of the cable when all cable pairs are energized, or a 5 degrees Celsius reduction in the maximum ambient operating temperature of the cable when half of the cable pairs are energized. Additional cable ambient operating temperature guidelines for Type 2 operation are provided in ISO IEC TR 29125 and TIA TSB 184. I don't know what the fuck that was. As a result of these considerations, one recommendation is to avoid high temperatures around the cable bundles and to ensure that the operating temperature around cable bundles doesn't exceed 50 degrees Celsius, which means 122 degrees Fahrenheit, which is fair, I feel like. The cabling considerations for PoE are described in separate standards documents. The 2 documents cited by the IEEE include a technical bulletin called TSB 184 Guidelines for Supporting Power Delivery over Balanced Twisted Pair Cabling, which is available from the Telecommunications Industry Association, and an ISO standards document. I don't want to read out the ISO standards document names, they're so long. Information Technology, Telecommunications Cabling Requirements for Remote Powering of Terminal Equipment. I'll read that name. I don't want to read the like ISO IEC number, blah, blah, blah. Okay, this is available from the ISO. Both documents provide guidance to cable installers to help characterize the amount of heating that can be expected in the worst case, which means large bundles with lots of cables carrying a lot of power, and to ensure that a cabling system will work optimally when PoE is in use. The bottom line is that a small amount of heating occurs on any copper cable that carries power. The heating is not an issue for individual Ethernet cables, but when those cables are bundled tightly together in a cabling system, and if all cables are carrying the maximum amounts of power, then the increase in temperature could have an effect on signal quality, especially if ambient temperature around the cables is already very high. Under normal circumstances with cables inside a typical office building, the cables will function correctly. All right, PoE Power Management. An Ethernet switch that provides PoE over some or all of its ports can also provide a power management point for the network devices powered over the Ethernet links. While the PoE standard defines the mechanisms for sending direct current power over Ethernet cables, it does not define which options and other management capabilities vendors may implement in the equipment that they build. Nor does it define how those management functions may be designed or what the management commands may look like. Assuming that a management interface is provided, the documentation for your switch or midspan equipment is your source for the details on how the interface is organized and what commands it uses. Excuse me. As the PoE standard is defined to operate automatically, it's possible for a low-cost switch to provide a simple PoE capability that supports PoE operations, but doesn't provide a management interface. However, many vendors do provide a management interface on the PSE that allows you to do such things as control which ports provide power, turn power on and off a given port, and monitor power consumption per port. All right, PoE power requirements. As a user of PoE, it's important to understand that the power supply in the Ethernet switch or multi-ports midspan device will be a limiting factor. In other words, you can't provide more PoE power than the internal power supply of the PSE can handle. It's up to you to make sure that the PSE, which is typically an Ethernet PoE switch, has enough power to meet your needs. For example, a 24-port switch providing 802.3 AF PoE at 15.4 watts per port requires an extra 370 watts of power beyond what is required to run the Ethernet switching functions in order to provide power to all 24 PoE ports simultaneously. Woo! If those ports each provide 30 watts of 802.3 AT power, then the switch will need 720 watts of extra power capability for those PoE ports. Now, speaking of PoE Port Management, to help manage these power loads, vendors of managed switches typically program the switches to provision power one port at a time. Allowing the switch to power up one port at a time avoids having to provide full power to all ports simultaneously and potentially running out of power in the process. As an example of how PoE switches are designed to operate, one major vendor of PoE switches provides 3 power management modes that can be configured on the switchboards. Okay. I like how they don't name what the major vendor of PoE switches provides, or what that vendor is, right? If anybody knows, tell me. Okay, so our first mode, power management mode from this vendor is called Auto. With this default setting, the switch automatically detects if the connected device requires power. If the switch has enough power, then it grants power to the port, updates the power budget information, and turns on port power on a first-come, first-served basis. If granting power to a given port would exceed the power budget, then the switch denies power, disables power on the port, generates a log message, and updates the port's LEDs to indicate the status. Okay. Static is our next mode. With this setting, the switch pre-allocates power to a port, even when no device is connected, and guarantees that power will be available for the port. A port with a static power configuration doesn't participate in the first-come, first-served model of operation. Because power is pre-allocated, any device that uses less than or equal to the pre-allocated amount is guaranteed to be powered when connected to a port configured as static. The statically configured power level is not allowed to be adjusted. Oh, sorry. The statically configured power level is not allowed to be adjusted via power classification or messages carried by the CDP or LLDP protocols. Okay? And then our last mode is called Never. This configuration disables PoE detection and turns the port into a data-only port. Cool. All right, PoE monitoring and power policing. Vendors can also provide mechanisms for managing ports after they're powered. One major vendor's implementation includes power monitoring and policing. If a powered device attempts to consume more power than the maximum allocated on a port, then the switch can be configured to turn off power on the port or to just log the event and update the LED status light for the port. The power policing feature is disabled by default. When this feature is enabled, it uses several pieces of information to determine what the power limit should be. You can configure a maximum wattage level for one or more individual ports, or for all ports on the switch, which becomes the power level at which policing will occur. Or you can set an automatic or static switch power level on each port, which will allocate power dynamically or statically as you prefer. Finally, you can let the switch port automatically determine the power usage of the powered device. When power policing is configured, the switch polices the power usage sensed at the switch port, which is different than the amount of power that actually arrives at the powered device over the cable. The cable distance between the switch port and the powered device is responsible for some amount of power loss due to the resistance of the copper cable. If a device uses more than the maximum power allocated on the port, the policing function on the switch can be configured to take different actions. It can be set to turn off power to the port, or it can be configured to just generate a log message and update the status on the port LEDs. Did we not just read that exact sentence? Have I just completely zoned out? No. It's right here. It's literally the same. It's like slightly different, but it's the same thing. Okay, whatever. Just wanted to make sure I wasn't going crazy. Okay, Lemur tells us that power policing should not be confused with the overcurrent shutdown of capability in the PoE standard. Power policing refers to configuring a power level on a port and then having the switch take some action if that power level is exceeded. No matter what level you set, if a powered device consumes too much current and causes an overcurrent condition, then the PoE standard requires that the power be removed and that the port go back into power detection mode. When policing is enabled, a PoE switch can also be configured to manage the order in which ports are powered. If automatic power policing is configured, then the switch will enable power one port at a time using ascending port numbers. Port 1 will be powered first, then port 2, and so on. If it's possible for a switch to power off ports as well, God, my brain just stopped wanting to read properly. It's possible for a switch to power off ports as well. If a new module is installed in a chassis switch, for example, and that switch now has less power to provide to its PoE ports, then typically the ports will be unpowered in descending order, starting with the highest port number that's powered and working downward until the power budget is sufficient to meet the power required by the remaining ports. All right, so when we're adding power, we're powering things on, we start from the lowest one and move up. When we're powering things off, we start from the highest one and move down. Okay, we've got some vendor extensions to the standard. Interesting. Okay. All right, after 802.3 AT made it possible to provide roughly 30 watts over 2 pairs of wires, it was a relatively straightforward process to extend the standard to provide power over 4 pairs simultaneously. This approach provides roughly 60 watts of power by implementing 2 sets of 802.3 AT compliant electronics at each end of the link and powering all 4 wire pairs at the same time. When the new IEEE 4-pair PoE extension that's currently under development becomes adopted as part of the standard, so that's what Javier was saying, basically it already is now. It's been 7 years. It's now, I guess, possible to provide higher power using technology that will interoperate between multiple vendors. Until that happens, various vendors have provided their own solutions. Okay, so I guess this section is a little outdated, especially because now we have vendor neutral capabilities, right? But we'll just go through them anyway. Might as well learn about them. Oh, I remember this being mentioned in maybe the CCNA or Encore exam. I'm not sure. I remember this vaguely. Cisco Systems is one major vendor. I always forget that Cisco's full name is Cisco Systems. Everyone just calls them Cisco. Okay, they're one major vendor providing 4-pair PoE power, which it terms Universal Power over Ethernet, or UPoE. It's also extended the LLDP-based power negotiation protocol to allow mutual identification and dynamic power budgeting up to 60 watts. Cisco switches can be configured to statically set the port power budget to enable support for devices that don't know how to deal with Cisco's UPoE extensions. Okay. Microsemi EEPoE. Double EPoE maybe? I don't know which one's better. EEPoE, double EPoE. I like double EPoE, I think. It just rolls off the tongue better. Microsemi is a company that provides mid-span PSEs for PoE. It's also extended the 802.3 AT standard to provide power over 4 pairs of cables in an approach that it calls energy efficient power over Ethernet. So EPoE. Yeah, exactly. You got it. Destroy worlds. EPoE. EPO. Double EPoE? I don't know how they actually pronounce it, but whatever. Microsemi points out that mid-span PSEs can be upgraded without having to change your switching hardware, allowing an innovation like double EPoE to be implemented at lower cost, assuming you're already using mid-span technology. The advantages of this include more flexible power management than that provided by some PoE switches, as well as improved integrated circuits for PoE ports that minimize the power consumed by the PoE detection process, among other things. The vendor notes that 4-pair powering helps reduce power losses over the copper cabling, further improving energy efficiency. All right. Now we have PoE. PoE, Power over HD Base T. The HD Base T specifications are not part of the IEEE standard. Instead, they've been developed by the HD Base T Alliance, which was formed to help develop technology for use in home entertainment systems. Hence the use of high definition, or HD, in the specification name. The HD Base T system operates over Cat5e6 cabling to provide up to 10.2 gigabits per second of uncompressed video and audio signals, 100 Base T Ethernet control signals, and power on the same cable. PoE makes me hungry for pho. You're supposed to say pho, but yeah, everyone's brain, pho. The Power over HD Base T, or POH, portion of the system is based on the 802.3 AT standard and uses all 4 pairs of cables to deliver up to 100 watts of power over distances up to 100 meters for powering home entertainment systems. The Energy Star specifications, and I have to yawn randomly. The Energy Star specifications have been reducing the power required by television screens, with the most recent Energy Star 6.0 version limiting power consumption to under 100 watts for 60-inch screen sizes. This makes it possible to power many HD screens using the POH system provided by the specifications developed by the HD Base T Alliance. Oh boy. Yeah, this is out of date. Oh, 2014 and your technology. Hey, we made it to part 2. This is a huge milestone. I didn't think I was ever going to get there. I'm not going to lie, but we did it. But yeah, thanks for joining me. This was a good stream. I'm really sorry to everyone that I forced the fruit eating on in the beginning, but I'm not actually that sorry. I wanted to get out of the way. So good night. Thanks for joining. I love you. I will, I hope to, I don't know, talk to you soon.